Electromagnetics is a very interesting subject with a wide variety of real-time applications and day-to-day applications. This lecture is divided into 6 parts: the introduction, scalar and vectors and vector fields, vector algebra, vector products, vector components, and the coordinate systems and their various aspects. Electromagnetics can be regarded as a study of interaction between electric charges at rest and in motion. It can also be described as a branch of physics or electrical engineering dealing with electrical and magnetic phenomena. The main aim of electromagnetics is to understand the 4 Maxwell's equations and their applications, where E is the electric field intensity, D is the electric flux density, H is the magnetic field intensity, B is the magnetic flux density, J is the current density, and rho v is the volume charge density. There are 3 fields in electromagnetics: the electrostatic field, the magnetostatic field, and the electromagnetic or the time varying field. The electrostatic field is produced by charges at rest. The magnetostatic field is produced by charges moving with uniform velocity, or it can be produced by DC currents or steady currents, while the electromagnetic or time varying field can be produced by accelerated charges or AC current. Electromagnetic field theory has a wide range of applications ranging from agriculture, defense, satellite communication to X-ray machines. Vector analysis is a mathematical tool with which electromagnetic concepts are most conveniently expressed and best understood. It can also be described as a mathematical shorthand or a concise language which greatly facilitates the analysis of electric and magnetic fields. Coming to scalars and vectors, any quantity can either be a scalar or a vector. A quantity is said to be scalar if it has only magnitude. Examples of scalar quantities include time, mass, distance, temperature, entropy, electric potential, population, etc. A quantity is called a vector which has both magnitude and direction. Examples include displacement, velocity, acceleration, force, pressure, electric field intensity, magnetic flux density, etc. It is customary to represent a vector by either a letter with an arrow over it, or in most books it is represented by boldface. Here in our lectures we will represent them by boldface. On the other hand, a scalar is represented simply by a letter. Field, it can be described as an area where a natural force is felt or has an effect. If the quantity is scalar, then the field associated with that is called a scalar field, while if the quantity is vector, then the field associated with that is a vector field. Examples of scalar field includes temperature distribution in a building, sound intensity in a theater, electric potential in a region, refractive index in a stratified medium. On the other hand, examples of vector field include gravitational force on a body in space, velocity of raindrops in the atmosphere. Coming to the third part, which is vector algebra, we will start with unit vector. A unit vector along a vector A is defined as a vector whose magnitude is unity and whose direction is along A. That is, a unit vector along A is defined as a vector whose magnitude is unity and whose direction is along the vector A. It is given by equation 1.5. And a vector A in Cartesian coordinate may be represented by equation 1.7, where capital AX, AY and AZ are the components of vector A in the X, Y and Z direction respectively, while small ax, AY and AZ are unit vectors in the X, Y and Z direction respectively. In figure 1.1, we can see the unit vectors AX pointing in the direction in which X is increasing, AY pointing in the direction in which Y coordinate is increasing, and similarly it is true for the Z axis. Any vector A can be broken up into three vector components, one along the x-axis, other along the y-axis, and the third along the z-axis. The magnitude of vector A is given by equation 1.8, while the unit vector along A is defined by equation 1.9, that is the vector upon its magnitude. Vector addition and subtraction. Two vectors A and B can be added to give the resultant C given by equation 1.10. When we add them, it has to be done component by component. The same is true for the subtraction process. D is equal to A minus B, and we can put it in the form of A plus minus of B. Again, the addition of the vectors has to be done component by component. Graphically, vector addition and subtraction can also be obtained by either the parallelogram rule or the head to tail rule. In figure 1.2, vector A and B are part of the parallelogram, and when we draw the parallelogram, the diagonal represents the resultant C. In the head to tail rule, the head of vector A is connected to the tail of vector B, and the resultant C is obtained by joining a line from the tail of vector A to the head of vector B. The same holds true for the vector subtraction also. Three basic laws of algebra obeyed by any given vectors are commutative law, associative law, and distributive law. For addition, all these laws are satisfied, while for multiplication, the first two laws are obeyed. Position vector of a point P is the directed distance from the origin O to the point P, that is, Rp is equal to xax plus yay plus zaz. In the figure, we can see for the point given by 3, 4, 5, the position vector is given by 3ax plus 4ay plus 5az. The distance vector is the displacement from one point to another. If we have 2 points P and Q and we want to find out the distance vector RPQ, then it is equal to RQ minus RP, and the output is obtained by adding the components of Q and P component by component. Vector multiplication. When two vectors A and B are multiplied, the output can either be a scalar or it can be a vector, depending upon how they are multiplied. Thus, there are two types of vector multiplication. Number one, scalar or dot product denoted by A dot B, and second, vector or cross product denoted by A cross B. When we have three vectors A, B, C, then multiplication of these three can result in either a scalar triple product or a vector triple product. The dot product or the scalar product of two vectors A and B, written as A dot B, is defined geometrically as the product of the magnitudes of A and B and the cosine of the smaller angle between them. Thus, mathematically, A dot B is equal to AB cos theta AB, where theta AB is the smaller angle between A and B. The result of A dot B is called either the scalar product because the output is a scalar, or the dot product due to the dot sign. If A is equal to AX, AY and AZ and B is equal to BX, BY and BZ, then A dot B is obtained by multiplying A and B component by component. Two vectors are said to be orthogonal to each other if A dot B is equal to 0. Properties of the dot product. Number one, it obeys the commutative law. Secondly, it obeys the distributive law. However, it does not obey the associative law. A dot A is equal to A square. AX dot AY is equal to AY dot AZ is equal to AZ dot AX is equal to 0. That is, the dot product of different unit vectors is 0. On the other hand, a unit vector when dotted by itself will give a result of 1. Cross product or vector product of two vectors A and B, written as A cross B, is a vector quantity whose magnitude is the area of the parallelepiped formed by A and B and is in the direction of advance of a right-handed screw as A is turned into B. Thus, mathematically, A cross B is equal to AB sine theta AB into AN, where AN is a unit vector normal to the plane containing A and B. The direction of AN can either be found through the right hand rule or the right hand screw rule. If A is equal to AX, AY, AZ and B is equal to BX, BY, BZ, then A cross B can also be expressed in the form of a determinant described by equation 1.18, which is obtained by crossing terms in cyclic permutation, hence the name cross product. Properties of the cross product: it is not commutative, rather it is anti-commutative, that is A cross B is equal to minus B cross A. It is not associative, it is distributive. A cross A is equal to 0. A unit vector when crossed by another unit vector will give another unit vector, that is AX cross AY is equal to AZ, AY cross AZ is equal to AX, AZ cross AX is equal to AY in the cyclic order. A unit vector AX when crossed with itself will result in a 0 output. Scalar triple product for three vectors ABC is defined by equation 1.19. It is the volume of a parallelepiped having A, B and C as its edges and is easily obtained by finding the determinant of the 3 by 3 matrix formed by A, B and C. Mathematically, it is given by equation 1.20. Since the result of this vector multiplication is scalar, the above equation is called the scalar triple product. Vector triple product for any three vectors ABC is defined as A cross B cross C is equal to B into A dot C minus C A dot B. It is obtained using the CAB and BAC rule. Components of a vector. A direct application of vector product is its use in determining the projection or the component of a vector in a given direction. This projection can either be scalar or vector. Given vectors A and B, we define the scalar component of A along vector B as A dot AB. In figure 1.8, we can see AB, the scalar component of A along B. On the other hand, the vector component AB of A along B is simply the scalar component in equation 1.22 multiplied by a unit vector along B. It can be noted that the vector A can be resolved into two components, one parallel to B while the other perpendicular to B. In fact, the Cartesian representation of a vector is essentially resolving the vector into three mutually orthogonal components as seen in figure 1.4. Till now we have considered addition, subtraction and multiplication of vectors. The division of vectors has not been considered because it is indeterminate or undefined except when A and B are in parallel. Coordinate systems and transformations. The quantities to be dealt in electromagnetic field theory are functions of space and time. It therefore requires thinking in the three dimensions of the real world, and therefore we must be able to define all the points uniquely in space in a suitable manner, and this requires using the appropriate coordinate system. A point or vector can be represented by any curvilinear coordinate system which can either be orthogonal or non-orthogonal. An orthogonal system is one in which the coordinates are mutually perpendicular. On the other hand, non-orthogonal systems are hard to work and have practically little or no use. Some of the examples of orthogonal coordinate systems are Cartesian system, circular cylindrical system, spherical system. Out of the 8, the first 3 are important and these will be used throughout the course. By using the most appropriate coordinate system, a considerable amount of work and time can be saved. The first of these coordinate system is the Cartesian coordinate system with which we are all familiar with. In this system, a point is represented by x, y and z. The range of the coordinate variables x, y and z are in the range from minus infinity to plus infinity. A vector A in Cartesian coordinate can be written as shown, where Ax, Ay and Az are unit vectors in the x, y and z direction respectively. It should be noted that Ax is in the direction of increasing x, Ay is in the direction of increasing y, while Az is in the direction of increasing z. Any point P given by x, y, z in the Cartesian coordinate system can be expressed as the intersection of three constant surfaces, that is x is equal to constant, y is equal to constant and z is equal to constant. X is equal to constant is the yz plane, y is equal to constant is the xz plane, while the z is equal to constant is the xy plane. For example, if P is 3, -2 and 8, then it is obtained by the intersection of the planes x is equal to 3, y is equal to -2 and z is equal to 8. Differential elements in length, area and volume are very useful in vector calculus. For Cartesian coordinates, the differential or incremental elements are dx, dy and dz. This incremental volume can be obtained by the intersection of 6 surfaces: x is equal to constant, x plus dx is equal to constant, y is equal to constant, y plus dy is equal to constant, z is equal to constant and z plus dz is equal to constant. The differential displacement dl is given by equation 1.25, which has 3 components, one along the x axis, the other along the y axis and the third along the x axis. Similarly, the differential normal area is given by equation 1.26. The area pointing in the direction of unit vector Ax is dy dz, that pointing in Ay direction is dx dz and that pointing in the Az direction is dx dy. The differential volume is given by dV is equal to the product of the 3 incremental elements dx, dy and dz. It should be noted that dl and ds are vectors while dv is a scalar. Also, the way ds is expressed is important. The differential surface element ds may generally be defined as ds is equal to scalar ds into unit vector an, where ds is the area of the surface element and an is a unit vector normal to the surface ds and directed away from the volume if ds is part of the surface describing a volume. If we consider surface ABCD, then it would be pointing in the direction of Ax and its area would be dy into dz. Similarly, if we talk about the surface PQRS, then its area would be dy dz, but it would be pointing in the -Ax direction. What we have to remember at all times about differential element is the incremental length, that is dl, and how to get ds and dv from it. Once we have dl, we can easily determine ds and dv. Looking at equation 1.25, the surface area along Ax is the product of the components of the other 2 unit vectors, that is dy into dz. The surface area pointing in direction of Ay is the product of dx and dz, while the surface area pointing in the direction of Az is dx and dy, while dv can be obtained as a product of the 3 components of dl, that is dx, dy and dz. The second important coordinate system is the circular cylindrical coordinates, which has rho, phi and z as its coordinates. This system is very convenient when we are dealing with problems having circular cylindrical symmetry. Here rho represents the radius of cylinder passing through the point P, phi represents the azimuthal angle, it is measured from the x axis in the xy plane, while z is similar to what we have studied in Cartesian system. The range of the coordinate variables rho, phi and z are given by equation 1.28, where rho ranges from 0 to infinity, phi ranges from 0 to 2 pi, while z ranges from -infinity to +infinity. A vector A in cylindrical coordinate can be written as given by equation 1.29, where a rho, a phi and az are unit vectors in rho, phi and z directions. It should be noted that a phi is not in degrees. It assumes the unit vector of vector A. For example, a force of 10 Newton acts on a particle in a circular motion, then that force would be represented by F is equal to 10 A phi. In this case, A phi would be in newtons. The magnitude of A in cylindrical coordinate system is given by equation 1.30. It should again be noted that A rho points in the direction of increasing rho, unit vector A phi points in the direction of increasing phi, and similarly Az is in the direction of increasing z. The unit vectors A rho when dotted with itself are output of 1, while when A rho is dotted with A phi, the output is 0. When A rho is crossed with A phi, the resultant is Az. Similarly, A phi cross Az is equal to A rho, and Az cross A rho is equal to A phi. The relationships between the variables x, y, z of the Cartesian system and the variables rho, phi, z of the cylindrical coordinate system can easily be obtained using figure 1.13. Rho is equal to under root of x square plus y square, phi is equal to 10 inverse y by x is equal to rho cos phi, while y is equal to rho sin phi. The table shown below is very useful in determining the dot products between various unit vectors and in determining one unit vectors, say Cartesian, in terms of other unit vectors, say cylindrical. In the table, for example, Ax dot A rho is equal to cos phi, Ax dot A phi is equal to minus sin phi, Ax dot Az is equal to 0. Similarly, Ax can be expressed in terms of A rho, A phi and Az as Ax will be equal to cos phi A rho minus sin phi A phi plus 0 Az. Relationship between Ax, Ay, Az and A rho, A phi and Az, which are components in the x, y and z direction in both the coordinate systems. As seen, A is equal to Ax plus Ay plus Az. Now we replace unit vector Ax by an expression using the table shown in earlier page. And when we solve that, we get equation 1.31. But A is also equal to A rho plus A phi plus Az given by equation 1.32. When we compare equation 1.31 and 1.32, we get the expressions for A rho, A phi and Az in terms of Ax, Ay and Az, which are depicted in equation 1.33. We can also have Ax, Ay, Az in terms of A rho, A phi and Az by using equation 1.34. Any point in the cylindrical coordinate system can be defined by the intersection of three constant surfaces. Rho is equal to constant, which is the cylinder, phi is equal to constant, which is the half plane, and z is equal to constant, the normal xy plane. For example, if p is equal to 3, 45 degree, 8, then it is obtained by the intersection of three surfaces: a cylinder having rho equal to 3, a half plane having phi is equal to 45 degree, and a xy or the z plane having z is equal to 8. The incremental volume in cylindrical coordinate system can be obtained by the intersection of 6 surfaces. Rho is equal to constant, rho plus d rho is equal to constant, phi is equal to constant, phi plus d phi is equal to constant, z is equal to constant, and z plus dz is equal to constant, as can be seen in figure 1.15. The differential displacement is given by 1.35, where the three incremental elements are d rho, rho d phi and dz. The normal area is given by, in the A rho direction, the area is rho d phi dz, in the A phi direction the area is d rho dz, and in the Az direction the area is rho d phi d rho. The differential volume is given by the product of the three incremental elements, that is dV is equal to rho d rho, d phi, dz. So, in this lecture, we have introduced the concept of vector analysis, which is a very powerful tool in expressing electromagnetics and for understanding electromagnetics. We have discussed scalars and vectors, vector algebra, vector products, vector components, and two of the very important coordinate systems, the Cartesian coordinate system and the cylindrical coordinate system. Hope you have enjoyed this lecture.